In this problem, they're giving us a chemical equation and telling us about both the initial number of moles along with the volume for a substance, and then they're telling us something about the number of moles at equilibrium. So they're giving us information both at the beginning and at the end of the reaction. Since we know this deals with equilibrium, it's always a good idea to start by writing an expression for the equilibrium constant K, since that's what they're asking for. Let's start by writing the concentrations of the products and raising them to the powers of their coefficients. So what I mean by that is there's an implied coefficient of 1 for N2 and therefore an implied exponent of 1 for N2 in the equilibrium expression. There's a coefficient of 3 for H2 in the equation and an exponent of 3 in the equilibrium expression. For the NH3, we have a coefficient of 2 in the equation and an exponent of 2 in the equilibrium expression. The other thing that we should note is what they gave us was a number of moles and not a molarity. When we consider the ice table that we'll have to make for this equation, we're going to use numbers that are molarity numbers, that is moles per liter. So it would be very helpful to come up with the concentration rather than just the number of moles. And I'm going to note that this is an initial concentration with that subscript 0 outside of the brackets. That subscript has no mathematical meaning. It just means that we're talking about conditions at the beginning of the reaction. So 4 moles divided by the volume that they gave us of 2 liters. 4 over 2, of course, is 2. So 2 molar is the initial concentration of nitrogen trihydride. Now for the ice table. First, let's rewrite the equation. And then we're going to list conditions as we were given them. So initial conditions, then we're going to track the changes in conditions, and lastly we'll list the equilibrium conditions. The reason we call this an ice table is because initial, change, equilibrium together spells out ice. Okay, so we've determined earlier that the initial concentration of NH3 was 2 molar. Let's list that in our ice table. They did not give us any information about the initial conditions of N2 or H2. And if they didn't tell you that, or anything about those initial conditions, it's safe to presume that they are 0. Many times a chemist sets up a reaction where you just, as the wording of this equation suggests, introduce a reactant into a reaction vessel, close the lid, and let things go for a while. Now for the change. Since we have a 0 in the initial line of the ice table, we know that we'll see a shift towards the 0. That is, the value of Q will be 0, and since K is always going to be greater than 0, that means that Q is less than 0, and so we have a shift right. The other easier way to look at that is just say shift to the side with the 0. That will always be the case. So that means we'll be adding on the right side of the equation and subtracting on the left side. How much will we be adding or subtracting? Well, we don't know, but we're going to define it in terms of x, noting that we have coefficients, and those coefficients get translated further down in the equation. So for instance, in the case of NH3, it's minus 2x because of the coefficient 2. And in the case of N2, it's plus 1x because there was a coefficient 1. And in the case of H2, it's plus 3x because of the coefficient 3. It's really important to carry those coefficients through because it affects your calculations. Now for the equilibrium line of the ice table. We simply take the initial line and add it together with the change line. So for instance, 2 minus 2x. That can't be simplified any, but I can write it all on one line in the equilibrium line of the ice table, 2 minus 2x. And 0 plus x, well, 0 plus x, that would just be x. 0 plus 3x, that works out to be 3x. So we have a beautiful ice table. Now we're going to take some of the information that they gave us in the problem and apply it to the ice table. Namely, they're telling us that at equilibrium, 2 moles of NH3 remains. So that means at equilibrium, the concentration of NH3 is 2 moles divided by the 2-liter container. So that's 1 molar. Going down to our ice table, now we have something we can work with. We now know that the expression 2 minus 2x is equal to an actual numerical concentration of 1. Now we have a simple algebra problem. If we subtract 2 from both sides, we get negative 2x equals negative 1. Divide both sides by negative 2. And we get x equal to 1/2, or 0.5. Since we know that x equals 0.5, we can now figure out the value of the equilibrium concentration of N2, which, if it's just x, it's 0.5 molar. And for H2, it's 3 times x. If x is 0.5, and H2 is 3 times that, that makes H2 1.5. We now have 3 equilibrium concentrations, 1 molar for NH3, 0.5 molar for N2, and 1.5 molar for H2. And we have an expression for the equilibrium constant. So let's just plug in the numbers that we have. For N2 it was 0.5. And for H2 it was 1.5. Remember to carry the exponent. So if there's an exponent 3, that needs to be carried through. And in the case of NH3, it was 1. And I guess in the case of 1, mathematically it doesn't matter if you carry that exponent through, but if it were anything other than 1, it does matter. So if we take out our calculator and punch the number in, this works out to be 1.69 for your value of K.